Welcome again for new class, my dear students. In the last class, we discussed some examples of quotient group and then try to find the quotient group, how to find a quotient group. In the end, I just prove one result where we show that G is a group and N is a normal subgroup of a G. If G is abelian, then the quotient group is abelian, and also provide a example where the quotient group is abelian, but there may exist a group G is not abelian. This means the converse of that theorem is not true in general. Also, we have to prove the converse of the Lagrange's theorem by using the quotient group. Now today in this lecture we have also discussed some other properties of a quotient groups. So let's start with this theorem. Let G be a group and N is a normal subgroup. And then if G is the element of a G and K is some integer, then N G to the power K is the same as a N G whole to the power K. You know, we can because G is the element of a G, N is a normal subgroup, so this means this can be written as N of G to the power K. I write in the form of N of G up to G. This is equal to K times because N is a normal subgroup, then by the property of a quotient group we can write in the form of NG again we have a K times, then we can say that the simple L is equal to Ng to the power K. So this is nothing but is equal to very trivial. So we have to there is a problem is this, we have a K is equal to Z. So this means we have three cases: K is greater than 0, K is equal to 0, and K is less than 0. If K is greater than 0, then this is the way we can prove this. Now if K is equal to 0, that is by induction is trivial. If we have to take N of G to the power 0 is equal to N of G. Now, so you just say that if you take N of G to the power 0 is equal to, you have a text right in the form of this. So this is the first part we have to prove, that when N is equal to K is greater than 0, then G by N is clearly. So we just take a N is equal to written as Ng, and this you have to write as a Ng to the power 0, and then we can write as Ng whole to the power 0. This is true when K is equal to 0. Now we have a K is equal to, we have a minus integers, this is M. We take M and M is N is equal to minus M, and M should be greater than equal to 0. So we have a N of G to the power N can be written as N of G to the power G inverse to the power M, and then this can be written as in the form of a N G inverse whole to the power M, and then we can write in the form of this again this can be written in the form on this form. So I just explain you a little bit. If we have a write into this form, so just this one. So this can be written in the form of this N of G inverse G inverse G inverse. This is equal to M times, and now this can be written as a by the property Ng inverse and G inverse up to Ng inverse. Again you have a M times, and then this can be written as a Ng inverse to the power M, and then by the property of this again this is nothing but is equal to Ng inverse is the same as a Ng inverse the same as a Ng whole ka inverse. So this means Ng inverse is the same as a Ng whole ka inverse. So this can be written in the form of a Ng ka inverse to the power M, and then again this can be written as a Ng to the power minus M, and minus M is equal to N. So this can be written as a Ng to the power N. So this means we can prove this result for the all the properties when the integer, because K is the integer, then k can be written in the form of a either k is equal to greater than 0, k is equal to 0, and k is less than 0. We have to just take it. We take some element where negative integer and take a greater than equal to greater than 0. Then on all the cases this result is prove this thing. Now next is we have to result is this, let G be a group and N is a normal subgroup. If G is generated by Z is cyclic, then G N generated by NZ is cyclic. So we have a giving a group G is a G group is generated by Z is a cyclic, and then we have to show that this G by N is generated by NZ, and this is also is a cyclic. And there is a some generators are there. So if a group G is generated by Z, then this can be written as some powers of this thing. So let G is generated by this, then we have to take some A is the element of a G by N. If A is the element of a G by N, then A can be written as a by the definition of A is equal to Ng. And now because G is the element of a G, and if G is the element of a G, G can be written as some power of a Z, Z to the power K, because the group is generated by Z. So G can be written as some Z to the power K, and then A can be written as NZ to the power K. And now again by the previous we have to show that this can be written as a NZ to the power K, because again this is the same thing we have to using NZ, Z, you have a K times, and then again using the NZ and NZ up to NZ again K times. So we can say that is the same as NZ to the power K is generated by N. And now if A is the element of this G by N, then we show that G by N generated by N of Z. And if Gn is generated by some power of a Nz, A can generated by an element of this generated by some power of a Nz. So this means this is clearly we can say that G by N is generated by Nz, and then so G by N is a cyclic. So clearly is a cyclic generated by some powers of a Nz. So we clearly say that G by N is again is a cycle. So G by N is a cyclic. Then if we go to the what about the converse? If G by N is a cyclic group generated by Nz, is it possible that is also is generated? However, the converse of a what about the converse of this theorem also is possible that we have to just say that if G by N is generated by Nz is cyclic group, is it possible G is generated by Z is also cyclic? So the converse need not be true in general, that is if G by N is a cyclic, then G may not be cyclic. So we have to find a certain examples where G by N is a cyclic, but G may not be a cyclic. I just use the same example. I think we have to showing the G is equal to generated G is equal to we have a S3. Okay, S3 is clearly this is not a cyclic group because there is no element which can be generated. Though because this you have to know that the order of these three elements of a is equal to 2, and order of these two elements is equal to 4, and there does not exist as any element of order 6. If it is does not exist any element of order 6 in this, so this means clearly this S3 is not a cyclic group. So S3 is not a cyclic group. Clearly one thing is clear. Now we have to find a N. You know that N we have to take in this form E 1 2 3, then 1 3 2, and clearly this is a we have to already show this many times. This is N is a normal in G, and then we have a G by N, and now you can find the G by N, and then G by N is generated by any one of the elements of this thing. So G by N we have to write because this is N. N can be written as in this form. So N is clearly is a normal subgroup of a G. So G by N can be written as equal to 2, and you know that G by N is a every group of a prime order is cyclic, so G by N is a cyclic, and then clearly G by N is so we can find the G by N is equal to cyclic group, and then we have to just show that this is N, G by N is the form of N of N, and N plus any one of them element which is generated this form. So clearly we find that this every any group of a prime order is cyclic, and then but G is a non-cyclic group, but we have to show that G by N is a cyclic. So this means if we have a G is a group, N is a normal subgroup, and G is generated by G is a cyclic, then G by Z G by N is also cyclic, but in the converse G by N is a cyclic. There need not be true where there may be exists as a non-cyclic group where G by N is a cyclic. Okay, so now we to move to the next result. In this result we show that if G is a group, then G by ZG is the center of a group. This is a so if G is a group and G by ZG is cyclic, then G is abelian. Abelian. First we show that if we show that this means this is a meaning only in the case if we show that this ZG is normal to G. So it's normal to G, we take any element of a G and X is the element of a ZG. Then we have to show that G X G inverse is also belongs to the Z Z of a G. So let's we have to try. We just take a because we have to show into this form. So we take a G in the form of this G X G inverse. X is the element of a G, so this can be written in the form of a G inverse X, and this can be written as a E of X and is equal to X. X is the element of a Z. So this implies that we show that Gx G inverse has the element of a Zg. So if G inverse G has the element of a G, then we can say that Gx is equal to also Gx is equal to we can say that X of G like this. So this means clearly X is Z by G is is clearly is a meaning. So this means we show that this Zg is normal in G. So this if normal in G, then G by Zg is meanings. So now we have to show that we have given that this G by Zg is a cyclic. If G by Zg is a cyclic, then this is generated by G, this element Zg G for some G is the element of a G. So we have to show that G is abelian, so means we have to take any two elements of a G, and then we show that G of H is equal to H of G. So A and B are the element of a G, then ZA and ZB are the element of a ZG. Now we have to show that we have to show that AB is equal to BA. So we starting from the this because these two are the elements of a ZG. So we write ZA and then we have to because Z is generated by this is the element of a G, because you know that this we have to this is given we have a G by ZG is cyclic. So if it is cyclic, then G by ZG is generated by some Zg into some G, and then generated by this element, and this is the element of a Zg. So this can be written as a Zg some G to the power n, and then by the property of you know that A again this can be we write in the form of a this can be written in the form of a using so many times this directly we write in the form of a this clearly you can Zg to the power G to the power n can be written as a Z of G, G, Z of G, G and so on, Z of G, G n times, then we can write this as a form of a ZG, G, 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 G n times, and then we can write into this form. So clearly this Z of A in the form of this, and this is generated by this element. The ZA is the form of a ZG. Then similarly we can write as a ZGB is equal to also written in the form of a ZG to the power n, and then we have to some m, not m. ZB can be written in the form of some this ZG for some integers mn, and now we have to calculating the ZGA, ZGB, and this is nothing but is equal to, you know, that ZGAB, and also this is the same as a ZGG to the power n, ZGG to the power m, and this can be written as a ZGG to the power m plus n, and this can be written as a form of a m plus n. So we just write into this form. So this means this A can be written in the form of a x to the power n, B can be written in the form of this, where x and y are the element of ZG. Then AB can be written as x g to the power n, y g to the power n, then xy g to the power m plus n, and then we have to, because we have to write this x and y are the element of a ZG, x and y are the element of a, both are the ZG, then xy is equal to yx. This can be written yx g to the power m plus n, and this can be written y g to the power n, and x g to the power because again we have to take a this can be written as a y x to the power this can be written in the form of this y x g to the power m g to the power n, and then this can be written in the form this x is a commute with this, so y g to the power m, then we have a x g to the power n, and then this can be written in the form this is equal to b, this is equal to a. Then we have to finally we have to show that that if we have a ZG is a any element this, then the G by ZG, and then this implies that G is an abelian. The quotient group G by ZG, then we have to show that G is an abelian group. Okay, so now we have to question, we have to just say that we say the question show that there does not exist any non-abelian group G such that G by ZG is order 30. The order of this is equal to 36. We assume that there exists a group of order, quotient group of order 37. So suppose there exists a non-abelian group G such that order of this is equal to 37. Since the group of this prime order is we know that since group of prime order is always cyclic, and then we have to show that if G is a cyclic, then G by ZG is also a cyclic, and G by Z is cyclic, then G by ZG must be abelian. So this contradicts the given the hypothesis. That means there does not exist any non-abelian group of order, quotient group of order 37. Okay, so now we have to prove this result, generalize. Let G be a group of a P square where P is a prime number. If ZG is the center of a G is non-trivial, then G is abelian. So we have to take this, generalize this form. Let G be a group such as order of a G is equal to P and E is equal to ZG, then ZG is not equal to, clearly is not equal to empty. So we have to just say that by the Lagrange's theorem, either ZG is equal to P square or ZG is equal to P, means is a ZG is a clearly is a subgroup of a any group G. So if ZG is a subgroup of a group G, then ZG should divide the order of a group by the Lagrange's theorem. So by the Lagrange's theorem, we can say that either order of a Z G is equal to P square or Zg is equal to P. If order of a Zg is equal to P square, then we can say that this is the same as a order of a G is the same as a order of a Zg, and then we can say that G is abelian. So if G is equal to P square, then Zg is the same as a J, so G is abelian. Because G is the same as the central group, then commute with every element. So this means we can say that G is an abelian. Now if we have a G is equal to P, Zg is equal to P, then the order of this G by Zg is equal to P. So every every group of prime order is a cyclic. So G by Zg is a cyclic, and so if G by Zg is a cyclic, then G is abelian. We have to prove this right now. So this means if group G of order P square, where P is a prime number, then J is then Zg, if Zg is the center of a G is a non-trivial, then G is a abelian group. So now this complete the proof of this theorem. Now have to some examples we have to discuss in exercises. If H is a normal subgroup of a G and G is finite, then G by H is a finite. And also show by example that the converse need not be true in general for this question. So we have to giving H is a normal in G, and G is a finite, so order of a G is finite, so we can say, and then you have to show that G by H is also is a finite. So we just take a since G is finite, therefore G has only finite number of a distinct light coset in G. If there is a finite number of a distinct light cosets of H in G, so index is a finite. If index is a finite, then the size of a, you know that the size of a quotient group G by H is the same as the index, and the index is a finite, then the order of a G is also finite. So this means G by H is a finite. Now for the converse, we have to find an G by H is a finite quotient group for any infinite group. Take a G is equal to set of integer under addition. We take a G is equal to set of integer. This is then we have to take a H is equal to, we take a 3Z. Then clearly H is a normal in D, or D. This is we take it differently. If we take a if G by H is a finite, then we G may be infinite. For example, if we take a H is the form of a 3M, where M is the integer, is a normal subgroup of a Z by Z under addition, where Z is infinite. However, if you take this set of integer with the H, if you take this is the coset of this, we have to take a H plus 0 is equal to H. We take a H plus 1 is equal to, like this, you have a 3 plus 3, 3 plus 1, and so on. And then we have to take if F plus 2, and then this is the element of this, we have a 0, H plus 1, H is equal to 3 times M. So we have a, if we take a 0 plus 3, and then so on like this. And similarly, if H is equal to 2, then again we have to getting the H. So there is a H plus 2. Now if we take H plus 3, then we getting the H plus 1, H plus 4, and repetition is starting from after this word. So we have to take only the, we have to take 3 different right cosets are there. So if we take similarly, if we have to see there is a this, so Zg is equal to, we have this is a finite. So we find a quotient group of finite Scheimpflug group. This G may be a infinite. So that means we can simply say that if G is a finite, then G by H is also finite, but converse is not true in general. If we have to find a finite G by H group where G is a infinite group. Okay, so now we have to another problem. We have to show that let H be H and K be normal subgroup of a group G such that H containing K, then show that K by H is a normal subgroup of a G by H. Okay, so we have to try to this. Show that H is a, first we show that H is a normal in K. Since H is a subgroup of a G and K is a subgroup of a G and H is clearly the subset of a K, so clearly H is a subgroup of a K. So clearly this is H is a subgroup of a K. And now we take a, for normality, H is the element of H, K is the element of a K, and then KH, K inverse is the element of H. Since H is a normal in G, we have a given. For H is the element of H, K is the element. Now we can say that H is a also is a normal into, because we have to show that, then we can say that some K KH, K inverse containing into the H. So this means H is a clearly is normal in K. So this means this K by H is a meaningful. So we have to say that the one this means this is a meaningful, and then now we have to show that this because H and K are normal subgroup of G, so this is meaning already. So now we have to show that the K by H, any element of a K by H with this is a normal subgroup. So let X and Y are the element of K by H, and X is the written as a HK1, Y can be written as a H of K2, where K1, K2 are the element of a K. And then XY inverse is equal to H of K1, H of K2 inverse, then H of K1, H1, K2 inverse. Then by the property H of K1, K2, then this is the element of a K, and then we can say that this is the element of a H by K. So thus H by K is a subgroup of a G by H. So this means clearly one part we have to show that H by K, K by H is a clearly is a subgroup of G by H. Now we have to show that this is a normal. So let A is the element of a G by H, B is the element of a K by H, and then X is we can write in the form of H of G for some G, and B can be written as we have to write in the form of a H of K for some K is the element of a K. So A can be written as some FHG. So A, B, A inverse. So we have HG, HK, HG inverse, and then HG inverse is equal to H of G inverse. HK, this is can be written as a by these two H of GK and H of G inverse. Then this can be written as a similarly this H of GK G inverse, and now you then know that the GK G inverse is the element of a clearly because since we have to show that this is a K is a normal in G, so this means GKJ inverse is the element of a K. This means GKJ inverse is the element of a K. We are assuming that this is equal to GK inverse equal to some C. So AB inverse can be written as a H of C, and this is the element of a this is C is the element of a K, so K by H, and for AB are the element of a G by H, and B is the element of, we have to take a K by H. So K by H is a clearly is a normal subgroup of a G by H. So we have to show that clearly this is a normal subgroup of a G by H by the this we have to introduce. Okay, so one more problem I just say that by this is show by example that in factor group G by H it can happen that the AH and BH are the same, but order of AH and BH is not equal to, we use the this A is not equal to identity or B is not equal to identity. If we have identity, then it's trivial. So we take a non-trivial identities. So AH is equal to BH, but order of A and order of BH. We take a G is equal to Z6 and H is equal to 0, 0, 3. Now you can just take a Z6. You take element of a Z6. So I just take a Z6 is abelian. So if Z6 is abelian, then this condition is automatically hold, and H is a subgroup of it. Therefore, H is a normal in this. And then if it's normal is this means Z by 6 is a factor group. So this means clearly Z6 by H is a quotient group. So first one is we have to just say that this is a clearly this is a abelian group and H is a subgroup of this. Then clearly this H is a normal, and if H is a normal, and then though this means Z by Z6 by H is a factor group. Now we have to show that the order of A and order of B is not equal to sin if we have AH is equal to BH. We take A is equal to 1 and B is equal to, we have to take A is equal to 4. So we have to just say that the factor group, so we have to take A is equal to 1 and B is equal to, so AH is equal to 1H and 1H is equal to, you have a 1 and 4 because this group is under addition, and BH is equal to the 4H. 4H is equal to 4 plus 4 plus 4 plus 3 7 is equal to remainder 1 4 1. But you can see clearly this is AH and BH are the same clearly. Then order of A is equal to, you have a generated by A, so this means this is equal to 6. We have a 1 plus 1 plus 1 plus and so on, plus 1 is equal to 0 is only 6 times. So order of A is equal to 6, and then 4 we have to take a 4 plus 4 plus 4 12 is equal to 0. So this is order of a B is equal to, we have a 3, and then clearly we have shown that order of A and order B are not the same, but AH and BH are the same. So this the problem we have to solve this. Now I just try to solve one more problem. Let H be a normal subgroup of a finite group G, and let X is the element of a G. If the GCD of a order of H and order of a G by H is equal to 1, then show that X is the element of a H. This is very trivial. Again, let order of X we have a M and order of a G by N is equal to N. Then if Hx is the element of G by H, and then we have to just say that Hx is the element G by X, then H to the power, because order of this is equal to N, so Hx to the power N is equal to identity is equal to H, and if it is identity, then H of X to the power N, because this is same as a H of X to the power N, and then we have wrote that H of A is equal to H, implies A is the element of H, means X to the power N is the element of H. And now since GCD of M is equal, Mn is equal to 1, so there exists a integers T and Q, Mt plus Nq is equal to 1 by the property of this GCD. So hence X Mt plus Nq is the same as a X X. So we have this, sorry, this is the X to the power Mt plus Nq is equal to X to the power 1, and this implies that X to the power Mt, X to the power Nq is equal to X, and then you have to we have a X to the power M is equal to, you have a identity, so this means this is equal to, you have a identity, X to the power M is equal to identity, so this means X to the power N Q is equal to X, and then if X to the power N Q is equal to X, then means we can say that and now since X to the power N is equal to is the element of H, so we can say that and H is a subgroup, so H to the means this is the element of H, and this means X to the power this X to the power N is the element of H, and H is a subgroup, X to the power Nq is also the element of H, and this implies that, and this is equal to X is the element of H. This is the element of H, and hence X is the element of H. So we have to just writing this is a mistake here. This will be X is not here. This is a X to the power this M to the power PQ, and then we have a rest into this form. So this is clearly we have to prove this is a satisfy this. I just take one more problem. Let N be a normal subgroup of a G, then G by N is abelian if and only if X, Y, X inverse, Y inverse is the element of N. For all X, Y is the element of a G. So we just say that we have to G by N is abelian. So we have to take a very simple A, B are the element of a G by N. Then A can be written as a Nx, B can be written as a Ny. Then G by N is abelian, and this implies that AB is equal to BA, and then A is equal to Nx, and Y is equal to Ny Nx, and then this is given by the property written as Nxy. This is Nyx for all X and Y is equal to this. Then this can be written in the form of a because of this can be written in the form of if you have a n A is equal to n of B, then you have a B inverse is the element of a n. So this is xy, yx inverse belongs to the n, and then by the property of this inverse, xy, x inverse y inverse is the element of a n for all xy belongs to the G. So this completes the proof of this result. Now I just conclude by this result. If H is a subgroup of a group G, x square is the element of H. For all x, prove that G by H is abelian, and then we have to leave this as a exercise. So now I just stop. Proof of this is depend upon to the previous exercise, because G by H is abelian if and only if x inverse y inverse is the element of this H. By using this property, x square is the element of H, you can easily prove this problem, solve this problem. So now I have to stop today's lectures here. I complete the today's lecture, the portion of quotient group, and then in the next class we have to start the group homomorphism. Thank you very much.